We have some people online. Can you guys hear? Can you for the guys online, can you let us? Okay, good. Thank you. Okay, good morning, everybody. We're going to dive into chapter 4 today, and we're going to take us about 3 lectures, or maybe 4, depending on how you guys respond. I announced in the beginning that the recorded lectures are posted on the website. If you go to our Canvas front page, all the announcements, either announcements or syllabus or front page, you'll see the link. So I didn't post announcements every time, but it's generally posted about an hour after the lecture. So if you guys needed to listen to the record lecture, just do that. Or for some reason you miss a lecture, always go back to check it, okay? So today, we're going to jump on to diodes. So diodes is the very basic semiconductor component they're going to deal with. You probably have already heard either through other media or through our simulation lecture. We have diodes and op-amps, and we have MOSFETs, BJTs, and so on. Or CMOS, you probably have heard that as well. So basically, there are 3 fundamental components. One is a diode, the other one is MOSFET, the other is the BJT. And those are 3 kinds of fundamental components put together. You form other components like CMOS. CMOS is 2 MOSFET together, complementary, like PMOS and NMOS, right? And you have Darlington BJTs, where you actually have 2 BJTs together, and you have maybe some other like diodes, Zener diodes, and so on. But they are all made of these fundamental components. So we're going to spend today on diodes, and then after the first and middle term, we're going to jump into MOSFETs and BJTs. Right? So we basically cover the 3 basic components. And by chapter 7, we look at the really just a small signal application of different semiconductor devices. So last week we talked about semiconductor materials. We start from conductor, insulation, and in the middle there's a semiconductor. And at negative 270 some degree C, there's no current because all the things are bound together, all the atoms and the electrons. At the room temperature, those bonds tend to break because the room warmed up those atoms. And when they break up, they release electron. And when they release electron, there's free electron in the material, and then there's also a hole, because when it breaks, the electron escape and then leave the atom has 1 positive. So you have positive, negative, but overall, they're neutralized because the number of electrons equal to the number of holes. Now you dope some impurity, boron or phosphate. Those material, once you dope in there, they're going to bond with the silicon, but then they bond well. They either have an extra electron or extra hole. So if you dump a lot of atoms, impurity, it creates either a lot of electrons or a lot of holes. So the ones with electron, we call N-type material, negative. The ones with a lot of holes, we call positive material. This semiconductor material by themselves do not have enough, even though they have a lot. Sometimes we call it N plus, N minus, or P plus, P minus. P plus means a lot of positive, a lot of holes. By itself, it does not conduct. But when you put this P-type material and N-type material, it forms the pin junction. Now, between the junction, the positive particle is going to try to move, and then the electrons are going to try to move to the other direction. So they form a depletion region in the p-n junction. And now if you apply external electrical field, which is a voltage, current will start to flow. But if you apply voltage in the other direction, it will not flow. That's reverse biased because the electric field is opposite to the two type materials. So in this lecture, in this chapter, we're going to talk about initially ideal diodes, really ideal diodes. They only flow current in one direction. There's no voltage drop. There's no current in the other direction. We don't talk about breakdown voltage and things like that. But then, of course, moving on, we're going to talk about the characteristics of a junction of diodes. Junction diodes means more like real diodes, like p-n junction diodes. And then we look at a little bit on how to model the diodes. Sometimes we call it piecewise linear model, which is also sometimes called constant voltage drop diodes. And then we're going to go to the small signal models a little bit on small signal. So the reason is that when you move from ideal diodes to constant voltage diodes to real diodes, there's steps to move from one to another, right? So, and then we're going to also talk about voltage regulation, rectifiers, and some other diodes applications. So that's the main contents for today. So let's start with a p-n junction we had last week. So if you have a diode, that's the symbol of a diode. It's an ideal diode. The ideal diode has a couple of characteristics. Only flow direction. So current, ID, one direction. So it's easy to know which direction because the arrow, like the triangle, indicate the direction of current. And voltage drop, VD is 0. Okay. So these are the two characteristics of diodes. So therefore, if you connect the diode to a voltage source like this, we're going to connect the voltage source voltage source to that. Because the diode only conduct current in one direction, which is supposed to be that way up on this right hand, would you see current in this circuit? So no current. So this is called, the current is 0. And this is called reverse biased, okay? Now we have another circuit. In this circuit, we know that current is going to start that direction. Would you have a current? Okay, and many of you will say, yeah, current can flow. But the next question is that how much is the current for ideal diode?
That an ideal diode that doesn't resist any current in the direction.
You're absolutely right. Because this is the ideal diode, the voltage drop on the diode is 0, which means you're shorting the voltage source. So ideally, the current will be infinity. Of course, so this circuit typically we don't like it. So we don't do this. Okay. Because now, of course, in order to avoid that to happen, we can do a different way. Instead of doing that, we can add a resistance. Okay. So let's say this is VD, this is V, this is R, this is D. So now we can define the current. So how much current would you see here now? So I is going to be V over R because the voltage drop on the diode is 0. Okay. And finally, if I have this, How much is the current now?
This side.
Yeah, the current is going to be IS because this is the current source, right? Of course, I'm going to just draw one more. If I have a current source like this, how much is the current here now?
Still IS. Because you flip both the diode.
Yeah, very good. I flipped both. Great. So maybe final one is
It's gonna explode.
it's going to explode because you can't have this because the current source has nowhere to flow. It will go really bad. But of course, to avoid that problem, what you can do is you can do this. You can have a voltage, you can have a resistance, and then the current, when it's kind of flow, it will flow here this way. Now, of course, I want to maybe dive into one more circuit just for illustration purpose. If we have this circuit over here,
That's the current source.
yeah, that's the current source. Okay, let me rejoin. Oops. Yeah, some students show me that they open the slides on Canvas, it doesn't work. You have to download and open it in PowerPoint because the writing, it gets, okay. So, yeah, with this IS, let's circle this just to this one. So you guys look at this circuit, how much will be current ID and I in relation to IS? Well, you have basically, I mean, you have current source and you have diodes in parallel with a resistor, but diode is an ideal diode, which means it's a short circuit. So current flow through the lowest resistance, it finds the easiest way to flow. So therefore, in this case, ID is IS, it's the same.
So diodes are just, they act the same as a wire, but it's just one way.
Yeah, it just conducts the current one way, but it's like a short circuit. Oh, interesting. What happened? Okay. Yeah, so now we can go more theoretically. How do you present a diode? Well, this is the symbol of a diode. And in ideal diode, as we said, that the voltage, when the current conducts, it's like 0. Of course, when it does not conduct current, okay, we forgot one, maybe we can do it here, is that when I is larger than 0, V is 0, voltage 0, current in one direction. That's the kind of definition of diode. But if you connect the voltage backwards, apparently the voltage is equal to whatever applied at the diode. It's reverse bias voltage, right? So that doesn't change, that current is 0. And if you look at mathematically, you can draw this, is like when the voltage is negative, no current. When voltage is positive, well, the current goes with whatever that current can be. So you don't really go to positive voltage because voltage is 0. So it's like when you guys are doing limitations, when voltage is positive, but it's not positive, it's like kind of that point is between 0 and positive, 0 plus. Okay, so I'm just going to draw one more to complement what we had on last slide, is that if you have a diode, actually, we're going to draw this one. So this is Vs. So the reason we draw this, because we said that Vd 0 when it's conducting, but now it's not conducting. So how much is this Vd will be? It will be negative Vs, right? So this is the only thing that I want to emphasize, that we write it this way. by definition. But of course, if you flip the definition, if you flip VD definition, then VD will be the same as VS. So so if we do it this way, I just want to also. So if we define this one to here, I'm going to call V2, I'm going to call it VD because VD is not defined that way. So V2 is going to be VS, and it's going to be minus VD. So if we define VD this way. So that's how you define a circuit. All of them are right, nothing wrong. But as long as you know what you define, just like a current, when you define this direction, your current flows the other direction, it's negative. Right? Voltage is the same. If you define this way, but voltage actually the other direction is negative. Yes.
Does the diode hold that voltage, or does it?
The idea diode in the reverse direction, yes, it would hold any voltage.
So you would have it kind of acts like a capacitor.
It's like a capacitor. Yeah, you're right. I mean, it's like a capacitor. Okay. Yeah, it is similar, but it's not a capacitor. It's blocking. Capacitor is actually, capacitor. Well, there's some similarity. Capacitor would store the energy. Yeah, right. In the capacitor, but this does not store any energy.
It immediately changes to the voltage. So if we disconnect it would not store any voltage.
Yeah. Well, for simple diodes, yeah, it would immediately change to that voltage, right? And there's no, I mean, think about it. You will still have some little bit of moving around before that happens, right? Dynamically, but in reality, there is no energy, so there is no charge, so there's nothing. But there's a kind of diodes we don't study in this book, but we studied in 584. The diode, what it's called? It's called a reverse. So when the diode reverses, you need to make up the lost electrons. So that way you do have some current going back to make up. Because let's say you have a diode like this with nothing connected, so it has electrons and positive and holes, right? So when you start to have current going through, the electrons move, the holes move, so the property changes within the material. But now, if you go from positive conduction, you suddenly want to move that to a negative, like blocking voltage, you have to make up reverse charge. So that is the current going back to make up the lost electrons to balance, like equilibrium. So that was what it does in that way, okay? So now let's go with some examples. In this example, we have 10 volts and a diode. So we want to calculate the current. So the previous circuit that I draw always have a loop, but now you don't have any loop anymore. But this is very typical in electronics book. They don't use any loop. They only use voltage up, ground down, or negative also voltage down. So in this case, because this is ideal diode, and you see that the 10 volts applied at the top, therefore there will be current. And then the current will be the voltage minus the voltage drop on the diode divided by the resistance. So it's 10 minus 0, which is 10 divided by 1K. That gives you 5 milliamps. So this is very simple. The current is equal to 10 minus VD over R and equal to 10 over 1K and equal to 10 milliamps. Now the next circuit, the top is the same, but we reverse the diode. So therefore, you know that the diode is going to block current. So therefore, there's no current. So there's no need to calculate. And we know that current over here is going to be 0 milliamp. Very simple, okay? But of course, since we get a little bit tricky, is when you have, let's say, you have sinusoidal waveform. On the top circuit, you see the VI is sinusoidal, which is sometimes positive, sometimes negative. Then you have a diode and you have a load resistance. In this case, we know that when the voltage is positive, it will conduct current. And the voltage drop is 0 on the diode. So therefore, you will see a voltage VO at the one VI is larger than 0, the diode conduct and so VO is equal to, because when it's conducting, the voltage drop on the diode is 0, therefore the output is actually the same as the input voltage. But when VI is less than 0, D is reverse biased. So therefore, how much VO? Well, there's no reverse bias means no current. No current in the resistor, therefore the voltage across the resistor will be 0. So therefore, if you draw the waveform, now it's already drawn here, you just simply corresponding these two, like one is positive, right? One is negative. So you see, so this is your positive waveform like this. That's your output. So also, you can draw the equivalent circuit. When the voltage is positive, diode is conducting, short circuit, no voltage, voltage 0. When the voltage is negative, diode not conducting, reverse biased, open circuit. So when you open circuit, there's no current. So therefore, the voltage is 0 here. I know, like in the past, the students have sometimes made a mistake saying, "Oh, this is the actual circuit. I can do a loop analysis, and I found that the voltage here is the same as the voltage here," which is totally wrong because there's no current. Okay. Now, where did the voltage go? Well, if you measure the voltage over here, you see what you get? That's a negative VI. Okay. So the voltage, where did it go? It went to the diode. Because the diode does not conduct current, it has a voltage. So in this case, if I want to draw the voltage across the diode, so this is the original voltage waveform, VI. So if I want to draw the waveform of VD, when it's positive, it will be conducting, so therefore VD is 0. And here, that's VD. So if you add VD and VO, oops, you got VI. You got VI. So this is important because, I mean, if you look at the top diagram, right? See VD, VO, VD positive this way, VO this way, VD plus VO equal to VI. So that's a loop analysis, very simple circuit. So ideal diode, another application or another example. What happens if you have 12 volts, well, a DC voltage on the output side instead? But of course, you can't have this voltage sources connect together without resisting in the middle just by a diode because, again, diode is 0 when it's conducting, so therefore you have trouble. So you have to have some resistance in between. So in this circuit, we have VS coming in, well, 100 ohm resistance with a diode and 12 volts. So in this case, if our VD, if our VI is larger than 12, what happens? If VS, we call it VS here, okay. Get confused, sometimes call VS, sometimes VI. So VS is larger than 12. Therefore, you see that the diode will be conducting because it's more than 12. And the diode voltage is 0, so all the voltage will be dropped onto the resistance, and you can calculate the current. Now, so we
just add sources.
What is it?
You just add the sources.
Add the sources together? What do you mean?
You would subtract the source.
No. Here, what I want you to do is here. I want to say Vx. I will call it Vx. I don't know. So I want you to find out what is Vx. So by looping analysis, you know Vx is going to be Vs minus 12, right? Or in other words, you say Vs equal to Vx plus 12 and plus Vd, and Vd here is 0. Okay, so that's why Vx is Vs minus 12. Now Vs is sinusoidal waveform. Therefore, really, what you're doing is just simply shift that down, right? So that's what you see the little hat in the middle of the sinusoidal waveform peak. You move everything down from 12 by 12. So if Vs is less than 12 volts, it's not going to conduct. So Vx is 0. So therefore, the circuit drawing is like you only conduct here. The reason is that, right? So everything below 12, Vx is 0. Everything above 12, you use the source minus 12, you get the output voltage. So this is the same circuit, but we're going to draw it in a different way. Instead of taking Vx on R, now we're going to measure the voltage across the diode and the V plus. So we're going to see how much voltage would you get based on the input of Vi. So look at, if Vi is less than, they call it V plus. If Vi is less than V plus, if Vi is less than V plus, would you have current in the diode? No current. Okay. If no current, what would you see the voltage at the top?
It would just be the voltage to voltage Vi.
So if there's no current, it means like this is open, right? So like this is open. So if this is open, you can see it passes through. So VO is simply Vi. So this is for Vi larger than V plus, right? Okay. So if Vi is, oops, I did it wrong. Vi less than Vi. So if Vi is larger than, if Vs is larger than V plus, what happens now?
It becomes.
So the diode is going to conduct. It's going to have conductor current. And it's going to conduct current means it's going to be 0 voltage. It's a short circuit. So here, you see here, you guys see it's a short circuit. If it's a short circuit, you can see this VO is immediately just as V plus. Okay. So if we plot the relation between VO and Vi. So we see here, if VO is less than, if Vi is less than V plus, if VO is less than V plus, so we're going to have to define where V plus is. So this, if Vi is less than V plus, which means in this area, this is Vi. So this is V plus. If Vi is within this region, VO is equal to Vi. VO here. Equal to Vi means it's going to be a 45-degree line. So you got here. Okay. So when Vi is larger than V plus, which what we do is Vi is here, Vi is this direction. Larger than V plus means it's going to go this way, and our VO is going to be equal to V plus. V plus here. So this one turns around like this. Now, one question is that what happens if I is negative? What would you get?
It would still,
What?
still be, that V out would still be DI.
Right? If Vi is negative, which means it's still less than V plus, so the output what you see is still Vi. VO is still Vi, so it's going to extend to the other direction. Means if Vi is negative, it's going to be VO is going to be negative as well. It's going to be same as Vi, so it's going to just extend. So now I give you guys a question or kind of homework to think. So when Vi is less than V plus in the positive region, or VO is same as Vi, when Vi is larger than V plus, we get output same as V plus. And in the negative region, if Vi is less than if Vi is less than 0, or VO is same as Vi, but it's going to go all the way, whatever Vi is going to be. Now, if I want to make sure that this Vi does, when Vi goes to very big negative, my VO is not going to go same as Vi. It's going to like this. Somewhere it's going to get flat. What would you do? Yes.
Could put another one of these circuits, but ups the other way around.
Very, very good. See, what you need to do is you would simply add, instead of doing one diode, you would do another diode. So for this circuit over here, I'm going to circle this. The output is going to be, oops, this doesn't look good. Okay, so if you have the diode flipped like that one, but just simply flipped it, it's going to limit, because when Vi is negative, means it's going to go this way. If it's larger than this voltage, current is going to go through. So you have the output is limited by this one. So we call this limiter circuits. You can limit the output to V plus when input goes big. Not many applications for this, but it's just ideal that you can limit your output regardless of the value of input by doing sort of voltage and diodes combination. Okay. Yeah.
You can explain more of the steps on how you knew that when Vi is greater than V plus and then that current flowed out. Just maybe go through some more. I just don't understand why that's the case. Why when Vi is greater than V plus, that the diode could let current through. I mean, it's just something simple in this.
Oh, well, if Vi is more than if Vi is more than V plus,
it's that the voltage across. So if you measure the current can only go through when the voltage across the diode.
Right. So this is really the fundamental. Let me see. Okay. This is really. Let me do maybe some space over here. So what happens with the diode is when there is potentially positive voltage applied to the diode, it's going to conduct current, and when it's conducting, the voltage is 0. So if you are not sure why it's going to conduct, what you can do is you can assume it's not conducting. See what happens. Let's say in this case, if you assume the diode, let's say, okay, now you have 12 volts over there, and you have Vs, and then we're going to do a few examples. Let's say Vs is going to be 15 volts. Let's say we will start with Vs at let's say 5 volts. Okay. Now, you see, if Vs is 5 volts and this is 12, so assume this is not conducting, assume it's not conducting, and then the voltage on the left hand of a diode is how much? Is 5, right? On the left hand is 12. So 5 minus 5 is less than 12. So this diode is not conducting, which confirms your hypothesis. So you start with your hypothesis saying this diode is not conducting, and then you verify whether it's correct.
Higher voltage on the other side that can't like.
Well, the voltage across the diode is negative.
Yeah.
Therefore, it's not conducting. 5 on this side, 12 on that side. So 5 minus 12 is 7, minus 7, right?
So
Okay. So it's,
treat the diode as an open. It will only conduct
Yeah.
when the voltage is appropriately.
it is 5 minus 12 is minus 7.
If you treat the diode as an open, it will only conduct if the voltage is.
So it's called reverse biased, okay? Now let's say Vs is 15 now. If you're not sure in the beginning, especially when we move on, actually, we have examples to talk about it. If you're not sure if this diode is actually conducting or not, you can always assume it's not conducting. So assume, like make your hypothesis. Say, okay, I don't know. So I just assume it's not conducting. When you assume it's not conducting, see what happens. Assume not conducting. If you assume not conducting, how much VT would you see? On the left hand, you see how much voltage. No conducting means no current, right? No current is no voltage drop on the 100 ohm resistor. So on the left hand, you see 15 volts. Not VD, sorry. VD is equal to 15 minus how much? 12. It's 3 volts. 3 volts larger than?
But must be.
So must be conducting, yeah.
So then there's not actually 3 volts across it because it's.
Well, for ideal diodes, there is no voltage, right? Once conducting, there's no voltage. Now you can calculate current. 15 minus 12 divided by 100, whatever, you get that current. So you can always do that. The good that you ask that question because in the future we're going to do that. Now I already explained the limiting circuit, so now you guys can look at this later. Yeah, go ahead. No. This is only limiting voltage. Well, certainly it will be related to current, but it's not. Current limiting is a different circuit. Yeah. Okay. So now this gets to a point that we want to discuss. Oh wow, you have to. How do I know it's diode? Okay. Well, I have no clue. I have no clue which one is going to conduct, right? So the only way to finally know which one is conducting, which one is not conducting, is to start by assumptions, because you don't know, right? I mean, even I look at it, I don't know even which one is conducting because truly, it's hard to know. So this two circuits actually is slightly different. The difference is that we flip the resistance. On this one, you have 12 up, 6 down. The other one has 6 up, 12 down. Yeah. Oh, okay. Do you assume what? Little to no resistance? No, ideal diodes. Ideal diodes, no resistance. For example, there's no resistance, right? No voltage, no resistance for ideal diodes. But of course, Thursday we're going to move on to piecewise linear model. There is resistance, there is diode, but so we go from simple to more complex. Yeah. But for now, assume, yeah. So what we can do is because there are 2 diodes, right? So you can do, there are 4 different combinations. So D1 on D12, D1 on D12, D1 off D12, both on, both off, 1 on, 1 off. So you have 4 diodes, you have 4 different combinations. So if you're lucky, your one combination, your one assumption will solve the problem. If you're not lucky, you might actually get down to 4 assumptions and the final one is correct. But of course, sometimes once you are familiar with diodes, often you will have some preliminary you have some preliminary ideas about what's going to happen. Like in this case, you have voltage 3 up, minus 3 down, and both diodes downward direction. So you know that it's not possible for both reverse bias, right? Because there has to be some current flowing from positive to negative. So right away you eliminate one possibility. Right? But then, of course, between one on, D1 on, D2 on, or both on, we will have to make an assumption. So let's start making an assumption of D1 is on. See what happens. I'm going to separate this two sides. So for this one, assume D1. Sometimes in the future, we simply call it on off. You can also call it reverse biased and forward biased, but the simplest way is just called on off. On means conducting current, no voltage. Off means reverse biased, no current, full voltage, reverse biased voltage. Okay. So assuming D1 is on. So if we assume D1 is on, how much voltage would you see at V? Here we call it VO. So how much voltage would you see at VO?
0.
Then VO will be 0 because if D1 is on, D1's bottom is connected to ground, so therefore it's 0. So if VO is 0, how much current is in here? Let's call it I1, and then let's call this I2. How much is I1 now? I1 will be 3 minus 0 divided by 12K, right? 3 minus 0. Yeah, that's what current voltage across the 12K resistance. That gives you 0.25 milliamps, okay? And then how much I2 can you calculate?
There shouldn't be any current.
No. 0 to minus negative 3 divided by 6K. That gives you 0.5 milliamps. So this gets you to the critical point. You assume D1 is on, D2 is on. Well, actually assume D1 and D2 on, right? Yeah, we should assume this. Now you see there's a problem. Or maybe there is no problem. So which means I1 here is 0.25 milliamp. And the current here is the node over here. Okay, I want you guys to look at for a second. Do you see a problem? Yeah, what problem do you see?
That's fine.
Hmm?
Should have a sort of current at one, so there's not.
Okay, he said you have to have some sort of current D1 flowing out, right? To make up that 0.25, right? You guys agree? Yeah.
We have more current coming out.
The node, then the current coming into the node, right? Because if we assume D1 is conducting, but D1 actually should be current this way, kind of current up, right? Yeah.
I think that means
That means your assumption is wrong. So we have to redo it. Okay, so yeah, so we have to do one step by step. So, okay, so now, so it's wrong. Okay, now I'm going to erase this one so we don't get confused. Okay, so now, wrong, okay. Now assume, he said, you want to assume what? You want?
D1 is on and D2.
Okay, so you want to assume D1 on a D12, which current means I1 doesn't change, right? I1 is going to be the same, 0.25. Okay. Now, of course, that current can go to that I through D1, that's okay. But the problem is if D2 is off, what is the voltage at V?
-3.
-3, okay. So V equal to -3. But you have VO equal to, is it possible? Huh?
Because there's no current going through the resistor.
There's no current here. because he should assume with D2 off. D2 off with no current. If no current, 0 voltage drop -3, so this is -3. But this -3 will is 0. Is it possible? Is it possible? Anybody else?
Yeah, because there's could be a voltage drop across D2, it's in the opposite direction, right?
No. Why?
Well, you said D2's off, which means that
D2 is off.
it's in the opposite direction, right?
But
But this is -3.
yeah, we have.
So you have 0 -3. So you have 3 volts on the diode, which is not possible. You have 3 volts across the diode, not reverse. Because the bottom is negative, the top is 0. So 0 minus -3 is 3. You have 3 volts across the diode, which means not possible. So it's wrong. So now you've got to really, because we know that, one of them have to conduct, all two both conduct. So now we know you got really only one assumption left, which is D1 must be off and D2. That's the final assumption. So if D1 is off, we don't know VO anymore, right? Because D1 is off, we don't know VO. Now, if D2 is on, D1 is off, but you got a really nice loop circuit over here. You got a nice loop circuit. So you got 3 volts, goes through 12K. You have 3 volts, goes through 12K up here, but D1 is off, so there's no current here. Go through D2 because D2 on is a short circuit, and go to 6K. So we can now calculate the current I1 and I2. So I1 equal to I2 equal to how much, you guys tell me? It's going to be 3 minus 93 divided by
The total.
Yeah, 2 to 12 plus 6, it's a 6 divided by 18 gives you 0.3 milliamps. So we found the current. Now, of course, we like to do one more step to confirm actually our assumption is correct. Because what would you confirm is that because we assume D1 is off, right? Which means the voltage across D1 has to be negative. Negative means this is 0, which means the voltage VO has to be negative. If VO is positive, or something is wrong again. Okay, we're wrong again. Okay, I know it's right. We have to confirm it. So now we're going to calculate VO. How much is VO?
Well, no, yeah,
VO is going to be
you take the current and subtract the 12 ohm.
VO is going, yeah, 3 volts minus. Oh, what happened here?
Or alternatively, add the voltage. -3 volts.
Something is not right. Let me restart. So VO is going to be 3 volts minus the voltage drop on the 12K. Or you can be -3 plus the voltage drop on the 6K. That's both okay. So we're going to be, VO is going to be 3 volts minus 12K times 0.33 equal to 3 minus 12K.003 is how much? 4?
12 times a third.
12 times 0.3, 3.6, yeah? So it's minus 0.67 volts, which is correct. Correct. Which is possible, yeah, which is correct. Because now you know that D1 is reverse biased because the bottom is 0, the up is negative 0.7, okay? So apparently you see here, I mean, we start by assuming both on, and we not right, and we assume it's correct, and actually the last one we got it right. We're just not that lucky. If we are lucky, you got this one probably.
Well, we could have been more unlucky. We could have had both diodes.
Okay.
Which
So-
is possible. And
Now let's do another one. So this one will flip the resistance, and you guys can do the same procedure. Let's go I1 here, I2 here, and let's go to VO over here, or over here, VO. So again, we're going to assume D1 We're going to assume boson. Because again, it's not possible for boson because you have negative at the bottom, positive at the top. Yeah, go ahead.
Value for V is correct. 6K is 6K.
What is it?
Value for V, right? The question was really asking. It's just the current times the 6K.
The times, no, you mean the voltage here? No, you have to plus 3 here. So, yeah. So you either use this one plus this, or use that one minus that one. So
That's assuming that D1 is on, the V at that point is equivalent to the VO that we found, either way.
So in this case, we assume both D1 and D2 are. Right away, you know that the voltage VO is how much, like we did last time? Because D1 is on, so voltage 0, VO is, no, VO is 0, okay. Because D1 is on, so D1 is on, VO is 0, okay? Yeah, so if VO is 0, how much is I1? I1 is 3K divided by 6K equal to 0.5 milliamps. And I2 is going to be 0 minus 3 divided by 12K gives you 0.25 milliamps. And then now we know that I equal to I1 minus I2. I1 minus I2 equal to 0.5 minus 0.25. So because we assume D1 is on, and we do have a current going through D1, which is okay. So it seems that we got the right answer right away in our very first assumption. But if you're not sure, you can go on to assume two different assumptions. Like, okay, let's assume D1 on, D2 off. So if we assume D1 on, D2 off, if you assume D2 off, the problem is that if you assume, okay, if you assume D1 on, you know that VO is going to be 0 volts. You assume D2 off, you assume D2 off, right? So how much V would you get? So if you assume D2 off, means there's no current. If there's no current, how much would you see voltage at here? -3. Which means VD2 is going to be 0 minus 3. It's going to be 3 volts. That's impossible. So this assumption is wrong. You don't have to calculate current. So now we can also assume D1 off, D2 on. So if we assume D1 off, D2 on, this is a little bit complicated because now we know that the D1 is off, right? So we need to calculate current I1 equal to I2 equal to, again, 3 minus 3 divided by 6 plus 12. It's 18, 6 divided by 18 gives you 0.33 milliamps. So what we need to do is we need to calculate VO equal to 3 minus I1 times 6K, which is 3 minus 3 minus 2, right? Yeah, it's equal to 1 volt. CO equal to 1 volt means D1 has to be, so VD1 is going to be like 1 volt, right? So this is also not possible. So basically that's how you see you can calculate. Now for diode circuit like this, there's no easy way, especially in the beginning, because you really don't know which one is going to conduct. You have to do assumptions. And by doing assumptions, you'll be able to identify whether your assumption is correct or verified, or your assumption is actually wrong, and you have to redo the assumption. Yeah.
But regardless, the only one of the assumptions are gonna be correct.
That's, of course, yes.
There's not gonna be a situation where two assumptions.
No, if you got two assumptions right, you must have done something wrong in the mathematics.
Okay.
Yeah, in this case,
You could theoretically stop at this first one, right?
again, if you're not sure, you can do another assumption, just make sure, right? But theoretically, yes, if you're pretty sure that you did every math correct, you can stop. Yeah, like in this case, if you sure that you do everything math correctly, you can stop. But sometimes we make mistakes. Sometimes, for example, some students are still saying, well, I'm gonna have the voltage equal to 6 times the current. You forgot about this -3 here. Well, you say, oh yeah, so here is a positive, and that's 0. Okay, that's correct, which is wrong because there's -3 here. So -3 plus voltage drop here, this is actually still minus. So that's where you want to do more assumption than you should. Yeah, go ahead.
So if D1 is allowing current, is that just gonna be like a big short?
It's a short circuit, yeah.
ground?
Yeah.
And then there would be nothing else on the right side?
Right, that's correct.
Okay.
Yeah.
Okay.
Now, I just want to do like more examples. I mean, these examples are a little easier than the previous one. Okay, like this one. You don't have to do assumptions because this is only one diode, and the voltage up, bottom down units are. Now, of course, you're still not like okay, I just want to do from the very, very basic fundamentals that I want to see. Okay, well, you assume there's no current. What happens to the voltage over here? No current, 5 volts minus 0 on the voltage drop, you got 5 volts. And you got 5 volts across the diode, not possible. So it must be on. So if it's on, which means this is a short circuit. So you have 5 volts divided by 2.5K, you got the current you need, which is 5 minus 0 divided by 2.5K gives you 2 milliamps. And the next one, okay, so we need to go also V equal to 0. We need to find out. And then for the second circuit, you see the diode is flipped, which means there's going to be no current, right? So if there's no current, V is going to be is it going to be 0? Because that's where students start to make this. Oh, there's no current, so V must be 0. No, actually, if you say V 0, you're wrong because if it's V 0, there is a current across the diode. I mean, across resistance, right? So V is not 0, which actually is 5 volts. So only when V is 5 volts, the current over here is 0, right? Okay, the third one is, okay, this one a little bit tricky because we got everything flipped, right? So you got minus 5 volts here, and you got a ground up there. So if you're not sure, you can start to do the assumption. Okay, assume this diode is like not conducting, off. What happens?
The voltage across the diode would be 5 volts.
If you assume it's off, okay.
If it's off, the voltage across the diode would be -5 volts.
Assume off, and then which means the voltage across here. Oops. What they're doing? Okay, they're measuring the voltage across from ground to diode. That's how they're going to measure the voltage on this circuit, which is interesting. But if you assume it's off, which is the current is 0. If current is 0, voltage here, let me call it VO here. So VO is going to be minus 5 volts, right? And so V is going to be minus VO 5 volts, which means, okay, the diode has a reverse bias voltage of 5 volts, which is fine. Assumption is correct. So we don't have to continue. It's fine. But of course, if you want to just conform yourself, you can assume it's on. If you assume it's on, what would be the voltage VO?
It would
be 0, right? Because up is 0, so it's on, it's 0. So if that is 0, you would have current flow from 0 to minus. Now it's impossible because the diode does not conduct current in the reverse direction. So you got that verified right away. Yeah.
So I thought you said that a negative voltage is what we wanted.
No, depending on how you mark it. Well, in this case, a mark the ground is a positive. They mark the other side is positive. This side is negative.
So the line is the negative side of the diode?
Well, okay, if you want, the easiest way to understand it is that you want the arrow of current to point the same way as the triangle of the diode.
See, in this case, you can say VD is -5, right? So that's reverse biasing. So it depends on how you mark the symbols. You mark here, they mark positive up. So you shouldn't confuse, because what you're looking at is whether the voltage positive on the triangle the other side or on the flat side. Okay. Okay, last one. You have again same circuit but flip the diode. So now you see that 0 is up, negative is down. So most likely it's going to conduct. When it's conducting, what's the voltage? We 0 when diode conducting, and current is going to be 0 minus -5 divided by 2.5K. That gives you 2 milliamps. So which is correct. I mean, again, if you want to confirm yourself, you can say, okay, what happens if I assume it's off? If you assume it's off, means the voltage, if you assume off, this is -5, no current, no voltage drop. So here must be -5. You can't have a -5 at the bottom of the diode and 0 at the top, right? So that means this diode cannot be in the reverse bias direction. So going through 1 diode, 2 diodes, now we have 3 diodes. Again, ideal case. So this actually is fairly easy, even though there are 3 diodes. You might say, oh no, it's very difficult because you get 3 diodes. If I look, the combination will be on, off, 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 on, off, 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 on, off, 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 and then on, off, off, off. You get what? How many? About 9 combinations. You might say, if I do 9 combinations, that would be terrible because I spend all the time to do just one problem. Well, in fact, you don't have to, because ideally, I mean, in this example, when you do one assumption, you would right away get to know the second assumption. Like, let's look at, well, let's see. So in this case, you see there's 3 diodes, and each of them connect to 1 volt, 2 volts, 3 volts, and this ground is 1K. So we can get started by looking at from the bottom. Let's say if we assume this bottom diode is on, what happens at the voltage over here? If this is on, this is 1 volt. If this is 1 volt, of course you have current, that's okay. But look at the diode in the middle. You have 2 volts on the positive side and 1 volt on the negative side, which means it's not possible because this forward biased. So if the middle diodes, and then you got actually this will be 2 volts. So similarly, go up, it cannot be 2 volts because if it's 2 volts, the top one will conduct it. So now you say, okay, so my assumption, this arm is wrong, that arm is wrong, but the top arm seems to be okay, but we have to confirm. So if we say top is on 3 volts, and the voltage V will be 3 volts. So D3, D2, D1. So if D3 is on, and V is going to be 3 volts. Now V is 3 volts, and now you look at what happens to VD2 and VD1. So VD2 is going to be 2 minus 3 minus 1. You see here, now we use the correct symbol, minus 1, which means, okay, VD2, VD1 is equal to 1 minus 3 to minus 2. Okay, so which off, off, on. So it's that simple. I mean, look like a complicated circuit. It's actually very simple. So moving on to another circuit, we have 5 volts up and then 3, 2, and 1 down. So here, of course, we can do the same thing. We can assume D3 on, see what happened. So we assume D3 on, we have V is how much? V equal to 3 volts. If V is equal to 3 volts, we got trouble, because if V is equal to 3, and this is only 2, this cannot be 3, right? If this 3, and it will be conducting, once conducting, it will close to this volt, it will be 2.
We'll have a negative.
Yeah.
Have a positive.
Same thing here, if it's 2, it cannot happen because this must be on, because you cannot have 2. But when this is on, you get how much? So, which means it's wrong. So now we, at the end, we can only assume D1 on. So if D on, we got, so this is 1. So we got V is equal to 1 volt. If V is 1 volt, then we have VD2 equal to 1 minus 2 equal to minus 1 volt, which is okay, because off. And we have VD3 equal to 1 minus 3 equal to minus 2 volts, it's off. So here is how we mark the VD, okay? And here we mark VD. So which means it's off. So only VD3, yeah. Yeah, go ahead.
So they can't, so if they were all on, that means V would have 3 voltage values.
3 different wattage value, right? You cannot have it right. Right, that's absolutely correct. So of course, finally you can calculate current is equal to 5 minus 1 divided by 1K. It gives you 4 milliamps. And in this circuit, you have I equal to 3 minus, well, just 3 minus 1K. That gives you 3 milliamps. Okay, so those are very simple eventually circuit. I think we might have so I wanted to see if we actually well, this is actually exercise 4.4. So we did that all. We also did a video example 4.1. Let me see if I have more examples before we go into section, because on Thursday we're going to move on to section 4.2. We look at non-ideal diodes. Okay, so let me maybe do one more example, then we can get it done. Okay, so we're going to look at example. Okay, so suppose you have a circuit like this. Suppose you have a circuit like this. You have D1, D2, and you have a current source flowing down. Which branch do you think the current will go? Well, it will depend on the voltage at the 2 terminals. So if you have circuit like this,
Wouldn't we need a resistor?
no, not really. Suppose you have 2 like this. What do you think the current will be? Let's say this IS is 5 milliamps. And this current, this resistance, 2K, this is 3K. So guys, can you find the I2 and I1? Now in this case, what does the diode do here? You got 2 resistance, right? So the current flowing down, and then this both are connected to ground, which means the current has to go through the diode to ground and create a voltage drop. create a voltage drop. So can both diodes to be, it won't be off for sure, because if it's off, the current has nowhere to flow. So the current must be on, diodes must be on. So can one diode off, the other diode on, or can both to be on?
Since we don't know the,
Well, I give you the resistance value.
they both have to be on.
They both have to be on. That's what he said. And you say it can be. So actually, they have to be both on. The reason is, let's say if one is off, what happens? If that 5 milliamp goes through, let's say this is off. So that 5 milliamp goes to 2K. It creates 2 times 5 gives you 10 volts. It creates a 10 volts up there, which means also here. And 10 volts, and this no current means 0. The 0 is 10 volts, which means not possible. Okay. Similarly, if you assume this off, this on, you also have trouble because 5 times 3 gives you 15 volts, also not okay. So ideally, this 2 has to be on at the same time, and their current has to be proportional or inversely proportional so that they will generate the same voltage at the terminal. Okay, that's the point, right? If they, like you summarized very early on that, oh, you have 3 different voltages at one point, that's not possible. So they have to have same voltage. So because if they're both on, you simply take the diode and make a short circuit, which means these are 2 currents are in parallel, and this is the current divider. With the current divider, the current is proportional to the resistance in the other branch. That's 5 means this is proportional to this, which means this is going to be 3, and this is going to be 2. So 3 milliamps times 2 gives you 5 volts. No, 3, let's see.
3, and then the other one would be 3 minus 5 minus 3 would be 2 milliamps, and 2 milliamps times
6 volts, yeah, both 6 volts. So both, it's going to be, I1 is going to be 3 milliamps, and I2 is going to be 2 milliamps, and we over here is going to be 6 volts. I said 5 volts, that's wrong, so 6 volts. So you got same voltage, 6 volts, which is good. So this is how you connect this diodes, and now also, like in the book, for example, 4.8 have circuit like this. So in this case, if you look at the circuit, can you say this diode is on and off? It has to be on, because if it's not on, immediately you see that if it's not on, which means 2020 in series, you got 5 volts, you got 2.5 volts. And you got here 0, which is no good. So it has to be on. Once it's on, these 2 are in parallel. So it becomes 10K, so 5 divided by 30K, you got the current, and then multiply by the resistance, 10K, you got the voltage over here. So it's fine. This voltage, there's no voltage. I mean, what drop is 0 by itself.
So if it was a really large positive voltage at that bottom there, then it could be off because it'd be a negative.
Oh, you mean if there's a voltage here?
Like 20.
Oh yeah, if this, of course, if this is 6 volts,
It doesn't be greater than 2.5, right?
it has to be greater than.
Yeah, no, it just has to be greater than 5 because it would just.
It has to be greater than.
Resistor.
Yeah, it has to be greater than 5. Because if it's less than 5, some current will flow here. Well, we probably have to determine what exactly the voltage is going to be, because at some point you will find this has a negative voltage and it's no longer working. Okay, so you have to. Yeah. So so that's this circuit. Like sometimes, yeah, I think we're gonna just stop here, and then next week we're gonna move on to talk about non-ideal diodes. Okay.
Yeah.
And beyond that, then sort of the plastic fiber. Why?
Professor, did they leave a, that was like, I feel like I left some.